Hi, this is Mr. Mack. Now, I want to talk some about the derivative. First of all, we've defined the derivative, f prime of x, to be equal to the limit as h approaches 0 of f of x plus h minus f of x all over h. Now, sometimes we'll use the following terminology. In other words, you'll say the derivative with respect to x of some function f of x. And this notation right here is saying we take the derivative of the function f of x with respect to x. This would be another way of writing f prime of x. I just mentioned that because you're going to be, we use these notations interchangeably. Now, first of all, if we have some polynomial, let's just start with x to the n. If we want to find the derivative with respect to x of x to the n, that would be equal to the limit as h approaches 0 of x plus h to the n minus x to the n all over h, according to the definition of our derivative. Now, in your homework, you're going to be finding the derivative of some polynomial functions using the definition of the derivative and so forth. But let's just kind of take a look at what this would look like if we don't know what power n is. So we can say here, this is equal to the limit as h approaches 0 of x to the n plus, actually this is n choose 0, x to the n plus n choose 1, x to the n minus 1 times h to the 1 plus n choose 2, x to the n minus 2 h squared plus so on and so forth up to n choose n x to the 0 h to the n. And then, of course, we have minus x to the n, and this is all over h. Now, notice that, let's do a little more writing here. This is the limit as h approaches 0 of. Now, notice n choose 0 is 1, so we have 1x to the n minus 1x to the n. Those actually will cancel out. Now notice every other term has a factor of h in it. So we could take a factor of h out and we're left with n choose 1 x to the n minus 1 plus n choose 2 x to the n minus 2 h plus n choose 3 x to the n minus 3 h squared plus up to n choose n h to the n minus 1. Now, this is still all over h. Now, if you remember, since we have a, since we're evaluating a limit here, we can actually cross out the removable discontinuity. In other words, this h over h here can actually be gotten rid of because we're evaluating a limit. And then through direct substitution, notice if we put a 0 in for h here and over to here, all of these terms actually become 0, and all we're left with is this one term. Now n choose 1 is n, and then x to the n minus 1. So what we decide from this is that if we're taking the derivative of a power x to the n, then a shortcut is to say that it's going to be n times x raised to 1 power less than it was before. In other words, the derivative of x squared would be 2x to the 1. The derivative of x to the 5th would be 5x to the 4th, and so forth like this. Now we call this the power rule, okay? And let's just write it. The derivative with respect to x of x to the n is equal to n times x raised to the n minus 1. And this is the power rule. Now, let me point out that at the moment, we've just justified that this is true when n is a natural number. In other words, when you raise x to a power of 1 or 2 or 3 or 4 or stuff like that. Now, it turns out that this can be extended so that if n is any rational exponent or even any irrational exponent, if you have a variable raised to any real number, this power rule will still work. Let's just take a look. Now, let me just say, this is not a proof. This does not constitute a proof. This is just kind of an example to show you that what we're saying is reasonable. The proof of this probably is a bit beyond us at this point. Now, when we get to the point where we have done some more with the binomial expansion theorem, we can probably come back and look at this more, but the truth is we probably won't. So let's just do this. Let's find the derivative with respect to x of x to the 1/2, or in other words, the square root of x. Well, that would be the limit as h approaches 0 of x plus h to the 1/2 minus x to the 1/2 over h. Now, by the time you're watching this video, or shortly thereafter that, you're going to learn that evaluating limits, one of the tricks is to rationalize the numerator. And that's what we're going to do in this case. We're going to multiply numerator and denominator of this by x plus h to the 1/2 plus x to the 1/2 over x plus h to the 1/2 plus x to the 1/2. Now, we get the limit as h approaches 0 of x plus h minus x. In other words, we have a to the 1/2 minus b to the 1/2 times a to the 1/2 plus b to the 1/2. That's a to the 1 minus b to the 1. So that's x plus h minus x over h times, and I'm not going to do anything with this. This is x plus h to the 1/2 plus x to the 1/2, or at least I'm not going to do anything with it yet. Now, the numerator, the x minus x goes away, and so what we have left in the numerator is that h. And so again, since we're evaluating a limit, we can cancel out the h's and we're left with a 1. And now, by direct substitution, we can go ahead and put 0 in for h, and we get this is equal to 1 on the top. We have x to the 1/2, because x plus 0 is x, plus x to the 1/2, so that's 2x to the 1/2. Now, if you look at that in another way, that is 1/2 times x to the negative 1/2. Now, if you use the power rule, that we came up with, in other words, the derivative with respect to x of x to the n is equal to n times x to the n minus 1. Well, in this case, the derivative with respect to x of x to the 1/2 would be 1/2 times x to the 1/2 minus 1, which is 1/2 x to the negative 1/2. So that's a pretty amazing coincidence if it isn't true for all real numbers. And it turns out that it is. It's just a little bit difficult to justify at this point. So if you're having trouble with this, put that question on your back burner, and remember, once we get to the binomial expansion theorem, that we should go back and justify this. But by then, I think you'll be so totally convinced of it that it won't be necessary. All right, now the next thing that we want to do is we want to talk about derivatives of exponential functions. There's two schools of thought about how students learn calculus, or the way, the manner in which it needs to be presented. And one of the ways that it's presented is we do polynomial functions with derivatives and integrals, and then we come back and we introduce exponential functions. And the other way is to just go ahead and do them all at once. And our book does it the second way, and I think it's much better to do this. So now the question is, what is the derivative with respect to x of an exponential function? In other words, some a raised to the x. Remember here, the difference is that now the function has the variable as the exponent. Well, let's just take a look at what happens here. Okay, first of all, remember now, f of x is a to the x. Okay, so the derivative with respect to x of a to the x would be the limit as h approaches 0 of a to the x plus h minus a to the x over h. Now, we could do something like this. This is equal to the limit as h approaches 0 of a to the x times a to the h minus 1 over h. Notice there's a factor of a to the x in the numerator, and all I've done is I've factored that out. Now, this a to the x right here could actually go and sit out front. So we get this is equal to a to the x times the limit as h approaches 0 of a to the h minus 1 over h. Now the next thing we notice is that the limit, if we were to say we want to know the limit of a to the x when x is, or the derivative of a to the x when x is 0, then we would put 0 in for x, and and let's just call this f prime of 0. We would get that's equal to the limit as h approaches 0 of a to the 0 plus h minus a to the 0 over h. Well, a to the 0 plus h is a to the h, and a to the 0 is 1, and h is on the bottom. So notice this is the derivative of our exponential function at x equals 0. And compare that to this. So we could say that the derivative of a to the x, the derivative with respect to x of a to the x turns out to be a to the x times f prime of 0. Now, from here, we say, okay, now what are we going to do? Let's define, and actually you've been told what E is before, but now we're going to actually make a definition. What we're going to do is we're going to define E Euler's number to be equal to, now let's just make sure that I get this right. We're going to define Euler's number to be the limit as h approaches 0 of e to the h minus 1 over h. In other words, we're saying of all the bases we could have for the exponential function, of all the bases for exponential functions that we have, no, E is not this. We're going to define E to be, here we go. Excuse me. Of all the bases that there are for the exponential function, E is going to be the one where this derivative at 0 is 1. There, that makes more sense. All right. So in other words, if we go back up here and we say the derivative with respect to x of e to the x, it's going to be e to the x times the limit as h approaches 0 of e to the h minus 1 over h, but we're defining e to be the base for the exponential function where this limit is actually 1, so we end up getting 1 times e to the x or e to the x. Now what that means is, this is kind of important, is that e to the x is its own derivative. So the derivative of e to the x is e to the x. Now, that probably takes a little bit of meditating on, but think about this. The derivative of a function is a function that gives the rate of change, or the rate at which the function is growing at that particular instant. And e to the x now is the exponential function whose output is the rate at which the exponential function is growing at that instant. So e to the x is the function that is its own slope. E to the x is the exponential function that is growing exactly at the rate of the amount that is present at any particular time. That will take some meditating to kind of get used to. But that's going to be a very, very important concept as we move on. Now I'm going to close this video with that, and you should be ready to do the exercises on Chapter 3, Section 1. And there are some intermediate sections in Chapter 2 that I did not do videos on. You should be able to do those. It just didn't seem important enough to actually do a video. Maybe that's a problem, but hopefully we'll do all right with that. And so I'm closing this video. We're done. We're done.